welcome everybody to this episode of Augmented Intelligence Workshop. We usually don't have introductions for our speakers, so I will continue that policy. I will note that today has two legit computer science speakers, which is unusual for our group. Next week, I think we'll go back. Without further ado, so I don't eat into Tina's time, I would like to introduce to us Tina Eliassi-Rad.
Thank you. Thank you so much, Robert and Marina, for organizing this. Let me share my screen here. And I will try to be on time. And this is actually the first time I'm really giving this talk. This is a brand new paper that was published earlier this month, August of 2022. And it's with Xindi Wang, who is a graduate student at the Network Science Institute at Northeastern, who's now at Amazon now, and Onar Varal, who's a postdoc at Network Science Institute. Some of you may know Onar because he worked with Phil Mincer, and he's now an assistant professor at Sabancı University in Istanbul, Turkey. And so the talk is going to be about social and information networks. So you're all familiar with, for example, friendship networks or LinkedIn economic graph, or here I'm showing you the map of science. This is journals in different fields. The color is different fields, and then a paper in one journal citing a paper in another journal. This appendix here in white color nodes, that's humanities. The yellow is social science, and then this pink is computer science and electrical engineering. The purple is math, I think, and so on and so forth. So we're talking about these kinds of complex networks, and we're talking about information's spreading through them. So for example, you can think about if I'm friends with you, I'll tell you something, and then you may tell it to somebody else. Or with economic graphs, it's about information about jobs going forward and spreading. And so the question we wanted to ask was, what is the interplay between the network structure, what you saw in the previous slide in terms of nodes and links, and the spreading process when you care about information access equality? And I will define information access equality formally, but basically we will like the two groups. We're going to break our population into two groups. Usually you have a majority and a minority. So you can think about, I have this social network, and some of my nodes have higher socioeconomic standing. Some of them have lower socioeconomic standing. And so we're going to divide them into majority versus minority. And so we want the two groups to get the information at the same rates. So we wanted to ask this question, and recently there's been a lot of work on this. And so some of the common mechanisms and properties of networks that we know affect the minority nodes' access to information are, for example, preferential attachment, right? Everybody wants to attach to the star, or you may have heard of this in terms of the rich get richer. Homophily is another aspect of this, right? Birds of a feather flock together. Node activity, how active a particular node is, either on LinkedIn, Facebook, et cetera, and then also edge density. You can think of edge density as a dyadic relationship of the node activity. And just as a spoiler, as Robert mentioned earlier, I am a computer scientist. My background is in AI, machine learning, and data mining, but I'm not here to present a new algorithm. So usually in my community, it's like, look at my shiny new algorithm. It beats your crappy old 5-minute old algorithm, but I'm not here to present a new algorithm. I'm here to discuss an empirical study that we did on this equality of information access in network models with different growth mechanisms and spreading processes. And I will unpack this in a minute. So what are the growth mechanisms that we look at? We look at the dichotomy between the majority versus minority. As I said, in these social networks, we're going to assume that you have two mutually exclusive groups. One is the majority, the other one is the minority. And for now, you can assume that minority is just like if I have 100 nodes, right? The minority are less than 50% of the nodes, and I will quantify this, and the majority is the rest. Homophily, which I talked about already, which is birds of a feather flock together, preferential attachment, the rich get richer, and diversity. Diversity, you can think of it as how far away am I from segregation, right? How many, for example, links do I have between the majority class and the minority class? And then there are these spreading processes, and we're going to look at three particular properties of these spreading processes. One is whether the spreading process is simple or whether it's complex. The other one is whether the transmission rates are symmetric or asymmetric. And the third one is the various seeding conditions that you may have. And again, I will go through these in detail. And because this is Zoom and you may doze off, I'll just give you the spoiler up front in terms of what we found. And then if you need to take a nap, you can take a nap. So one of the things that we found in terms of the question that we asked was that information access equality is indeed a complex interplay between the network structure and the spreading process. So if you really care about information access equality, just changing the network structure is not going to be good enough. You really need to think about the spreading process on top of this network structure. The other thing that we found was that there's a trade-off between equality and efficiency of information access. These are under certain conditions. So for example, if you have a segregated society where there's low intergroup edges, and especially when you have these asymmetric transmissions, what you will see is that if you want the information to spread as fast as possible, then there's a trade-off between that and equality. And then what we found was that the features of the spreading process are in fact statistically significant when it comes to information access equality, so you really should care about them. But on the other hand, the network features are not always statistically significant. But two of them that stood out in our regression analysis was degree inequality and network distance. So degree inequality, you can think about, for example, the earth mover distance between the degree distribution among the majority group and the minority group of the nodes. And network distance, you can think of it as average shortest path or diameter of the network. And what are the impact of the downstream tasks here is that our findings can be applied to recommend connections that will steer an online social network toward information access equality for a particular kind of information spread, right? So ideally what you would do is you would first classify what your spreading process is. Is it simple contagion? Is it complex contagion? Is it symmetric transmission rate? Does it have asymmetric transmission rate? And then based on that classification, what you would do then is you would recommend new connections to your users such that for that particular information spread, you would move your network closer to information access equality. So now that I gave you the highlight of it, I'm going to go into the details of this empirical study that we did. And I see that there are a few chats, but I will answer them later. A few messages in the chat. So for the network models that we looked at, we started with the random network, and then we added preferential attachment to it. This is the rich getting richer, homophily, birds of a feather flock together, and diversity, this notion that I don't want a segregated society. And so they result in different generative network models. Some of you may have heard about Barabashi-Albert, which is a random network plus preferential attachment, and so on and so forth. And I will briefly go through these because I know this audience may not know about them, but it's incredibly important what generative processes are actually making your network. So for the random network, it's very easy. At each time step, a new node enters, and with probability m, it belongs to the minority group, and with probability 1 minus m, it belongs to the majority group. So if you think about, for example, the Facebook network, right, a new node comes in, and as opposed to connecting based on homophily, etc., with other people, it comes in with a random probability, and then with with a random probability, it gets assigned to the majority or the minority group, and then with uniform probability, it connects with L existing nodes. So a new node that comes in, it has L friends. And this is the growing version of the famous Erdős-Rényi network. Then in homophily BA, what is happening, BA stands for the Barabashi-Albert network, is that you add two more ingredients. You add preferential attachment and homophily. So now the number of parameters in your model increases. You have the proportion of the minority nodes in your network M. You have the number of new edges or new friends, if you want to think about it, that a new node will get. And then you will also have this doubly stochastic homophily matrix H, which tells you how likely is it for a majority node to connect to another majority node versus a majority node connecting to a minority node, or a minority node connecting to another minority node. And of course, this is symmetric, so we are not assuming directedness. So the homophily level for a majority node connecting to a minority node is the same as a minority node connecting to a majority node. And of course, you have this preferential attachment strength, this exponent that we're going to talk about. So for the homophily BA growth model, what happens is at each time step, a new node comes in with that probability M. It's a minority node with probability 1 minus M. It's the majority node. And then it gets a group membership because now you're dealing with homophily. So it gets a group membership. And now this new node J has to connect to L existing nodes in your graph. And the way that it connects, it's with a probability that both involves the degree of the other node and also the group assignment of the other node. We also modify this homophily BA to just be a random homophily where there is no preferential attachment, where this alpha, the preferential attachment exponent, is 0. And this is equivalent to stochastic block model, and you may have heard of it. And so just for your, if I make alpha being 0, then this becomes 1 and this becomes 1. So I'm not taking degrees into account when I try to find friends for this new node that has entered into the network. We also use homophily BA with random mixing where there is no homophily. So in this case, with the probability of connecting to another node would be 0.5. And then we added two other networks. One is network growth models. This is a diversified homophily BA where we are trying to encourage intergroup connections while maintaining some degree of homophily. Some of you may have seen the recent Nature article about how, if you have people from a lower socioeconomic class connecting to a higher socioeconomic class, then that is good for society. It was some work that Raj Chetty from Harvard had done. So what we're trying to do is we're trying to encourage this intergroup connections and discourage segregation. So here you will have even more parameters for the model. So in addition to the proportion of the minority nodes and the number of edges that a new node gets, and this homophily matrix and the preferential attachment, you also have to specify what are the number of diversified edges for every node, and what is this diversification probability. And so here at each time step, a new node will come in, again with probability M. It's a minority node with probability 1 minus M. It's a majority node that defines its group membership. Now, because you're trying to diversify, what you're going to do is L of LD, so L minus LD of the nodes, follow homophily BA mechanism. And then what you have is you have this LD, the number of diversified edges that you have. And what we do is we connect those so that we want this new node to connect to the opposite group, but with similar degree. So we don't want a new node, let's say a majority node, connecting to a minority hub, because that is typically unrealistic. And so what we would like is we would like to connect this new node to nodes of the opposite group, but we want to have similar degrees between the existing neighbors. So we want to have similar context between them. And then we also do the diversified homophily where you do not have preferential attachment. So this gives us all these different network models of how networks can grow. And now that we know how these networks can grow, we can talk about the processes that spread the information. And in particular, we only looked at susceptible infectious models. This is a compartmental model. The idea being is that you're susceptible to a piece of information and then you get infected by that piece of information. Perhaps you're susceptible to believing in the big lie and then you believe in the big lie. Now, one of the things which is interesting here is whether the type of information and the type of contagion that this is. Is it a simple contagion versus a complex contagion? Simple contagion is often more appropriate for diseases or spread of information versus versus complex contagion is more appropriate for collective behavior, such as spread of new technologies and innovations or spread of misinformation. And for those of you who come from the social sciences, you probably know about Mark Granoveter's weak ties. So weak ties are important when you have a simple contagion, but weak ties may not be useful when you have this complex contagion. In particular, because you need to hear this complex contagion from many people. And so we add a new parameter, this activation parameter A, where a node can only be infected if a portion of its neighborhood is infected. And then there's this notion of transmission rates. Is the transmission rate symmetric between all the nodes, or does a piece of information transmit differently between the different groups? So does a piece of information transmit at the same rate between blacks and whites, or for example, it has a higher transmission rate among whites than among blacks? And then finally, the last thing for the information spread is the location where the information is seated. Because different seating locations can advantage or disadvantage a particular group. Here, we are going to assume random seating in our empirical study. We're going to assume that you don't know a lot about your community to say, oh, well, if I spread it with John, that would be a better spreading. And then we're going to assume random seating, and we're going to investigate different proportions of minority seating. So I'm going to talk about low minority seating. That means less than 30% of your minority nodes have the information. Middle, which is between 30% and 70%, and high being greater than 70%. And because of time and because of similarity of results between mid and high minority seating, I'll only talk about high minority seating. Okay, so those are the processes. Now, what are the network measures, right? So there's network measures like homophily. In particular, I like this paper by Park and Barabashi that was published in PNAS in 2007, where they talk about dyadicity and heterophilicity, which is given a network, you count how many connections are there between nodes of the same type, and you normalize that by what you expected if it was a random connection. And heterophilicity is basically how many connections in your network do you have between different types of groups, right? Like if you have your nodes labeled as majority and minority, how many links are there between majority and minority nodes? And then you will normalize it based on what you expected that to be if your connections were random. And then we measure distance. This is average shortest path between nodes and the diameter of the nodes, the diameter of the graph. And then we have three different social capital or degree equality measures. One is the simple earth mover distance between the degree distributions of the majority and the minority nodes. The other one is this notion of power inequality, where you're looking at the average degree of the minority nodes versus the average degree of the majority nodes. And a lower power inequality means the more disadvantaged the minority nodes are. And then the last one is this moment glass ceiling, where you're looking at the second moment of the degree distribution. So as opposed to the average degree, you're looking at the second moment of the degree distribution, and you're seeing what is that for the minority nodes in your network versus what it is for your majority nodes. And here, the lower moment glass ceiling, the more disadvantaged, again, are the minority nodes. So let's look at all of these different network graph models that I talked to you guys about, and what are some of these kind of network measures on them. So as expected in the random network, the dyadicity and the heterophilicity is going to be 1. So what you observe is what you expected to observe if the connections were all random. Now, of course, in a real world network, the connections are not random, right? When somebody joins Facebook, it's not like they just randomly pick somebody and say, okay, I want to be friends with that person. In homophily BA, we observe that the heterophilicity is less than others. Again, this is because of homophily, that birds of a feather flock together. in diversified homophily BA, we're forcing these intergroup connections, right? We're recommending these intergroup connections. And so because of that, we see that heterophilicity increases, and the diameter is much also larger in the diversified homophily BA because of the encouragement of diversification. And in diversified homophily, we also have longer diameters. Here, you just don't have hubs compared to the homophily BA. Now, if we look at the degree distributions between the majority and the minority nodes here, we see that all the ones that have BA, this notion of preferential attachment, have exhibit this kind of heavy-tailed. And we can then see this when we measure the earth mover distance between the two degree distributions, where homophily BA, which is actually how most social networks get formed in real life, where you attach to somebody who's like you and you want to attach to a star, that is the least equal when you measure the earth that you have to move from one degree distribution to another degree distribution, versus random is the most equal between the two degree distributions. And if you look at the power inequality and the moment glass ceiling, one of the things that we see is that with diversified homophily, you're getting the most advantage for the minority group. And with a homophily BA, again, this is where most real world networks fall into homophily BA, you have the most advantage for the majority group. Now, how am I going to measure this information access equality? What we're going to be doing is we're going to inspect information access equality at different stages of the spreading process, because on different networks, it takes different amounts of time to do this spreading process. And so because of that, we normalize the fraction of the nodes that have been infected at each time step by the length of the spreading process. And so we get this delta I in terms of the change in the number that have been infected is between -1 and 1. Less than 1 means the majority group is the minority group is at an advantage. Equal means you have equality, this information access equality that perhaps you want, and greater than 0 means the majority group is at an advantage. And so I'm going to show you a bunch of results now after I've described how the simulation works. On the x-axis, we have different stages of the process. On the y-axis, we have the different models I talked to you about. I'm going to show you heat map. And blue is where you have the minority group is at an advantage, so less than 0. White is equality, and red, it means the majority group is at an advantage. So here, what you're seeing is we have these 4 different charts. So we have the simple contagion on the top row, we have the complex contagion in the bottom row. The first column is symmetric transmission rate, and the second column is the asymmetric transmission rate. And I know there's a lot of information here, but the main thing to take away is that if you do diversify the process that's making your social network, so if you do make recommendations that will reduce segregation in your social network, then you would reach equality faster, rather than if you had homophily BA or if you had random homophily. Remember, random homophily is homophily BA, except that you do not have preferential attachment. And one of the things that you will see over and over again is that with asymmetric transmission, regardless of whether it's simple or complex contagion, if you have high seeding in your minority nodes, what happens is that the minority is in an advantage, then you get close to equality, and then the majority gets advantaged. And then it becomes, then it gets to equality. This is, again, the advantage is the rate at which one group is getting the information. And so then we have a whole bunch of experiments that we did, and I am cognizant of the time here, where we looked at the different parameters. So how does this information spreading equality change if I change the levels of homophily? Homophily is birds of a feather flock together. And so as you would expect, if homophily is less, I would expect to reach equality that is this 0 or white cells a lot faster. Which is something we do see. However, again, if you have this asymmetric transmission rate, you have nonlinearity in your dynamics, and what happens is the minority node is in an advantage, then you get to a place where it's close to equality, and then there is a part where the majority node is in an advantage before you stabilize to equality. So it's not clear what is the right value of homophily when you have asymmetric transmission rate. We also looked at preferential attachment, and when your preferential attachment exponent here, the strength, is greater than or equal to 1, which is in most real-world networks, the type of contagion becomes very important, whether it's simple or complex. So again, you can't just interfere on the network structure and say, I can get information access equality. We also looked at a minority portion. So the influence of this M, the minority portion, is strongly dependent on the minority seeding portion. Like how much of your minority nodes are you going to seed to then reach information access equality? We also looked at the diversification probability, and obviously the higher the diversification probability, the lower segregation you have, the higher information access equality you're going to have. We also looked at efficiency. So initially I told you that one of the takeaway messages was that there is a trade-off between efficiency and access equality in certain conditions. And we see that especially in terms of asymmetric transmission, which is oftentimes the case in real-world networks. And because of that, we also see that diversified homophily and any kind of diversified model is slower in terms of spreading, and hence that trade-off. I'll just finish with some statistics on real networks. So GitHub is a GitHub follower network, DBLP is a collaboration network, and APS is a physics papers citation network. We got the data from the network inequality group at Vienna. For GitHub and DBLP, these are gender. Based on gender. For APS, it's based on the research field. Now, one of the things as a disclaimer, obviously algorithms are being used to decide the gender, for example, on an account on GitHub, and so there could be some noise associated with that. But one of the things that we see is that there are very few minority nodes in the GitHub follower network. We see a large amount of degrees, so average degree in DBLP. These are computer science papers that cite each other. And then we see that the dyadicity, you can think of it as homophily, among the minority papers in APS is very high. So the degree distributions in these real world networks are different between the minority and majority group. The minority groups have lower average degree. We know, for example, papers published by women don't get as many citations. And then there are fewer minority nodes that are hubs. This also corresponds to, like, for example, less people cite computer science papers published by women. So we also looked at information spreading equality of the networks. This is similar to what I had seen before, and we see that you have more equality, you reach equality in DBLP faster. There were lower homophily there. Then there's GitHub's smallest minority portion, and then APS, which has high homophily. We also did regression analysis. I won't have time to get through it. I already mentioned this, that network features are not always statistically significant versus the spreading process features are. And you can look at the regression table and details in the SI of the paper. Now, and I just want to finish with one thing. So this is an area in terms of fairness in complex networks. It's a relatively new area. These are some of the related works. There's just a few groups that I know of that are working on this. So Hong Tang at UIUC, Panayotis, they had a paper about fairness aware PageRank, where the amount of rank in minority nodes, you want it to be the same as the majority nodes. There's a lot of activity from the network inequality group at Complexity Science Hub in Vienna. I highly recommend looking at that. This paper is by my postdoc, who's now a tenured professor at Syracuse, Sujata Sandarajan, where they only look at the network structure and not the spreading process. And the one takeaway message here is that you should care about the spreading process as well. And then Anna Stoica at Columbia has done work on who should we seed if we want fairness in the social influence maximization. So just the takeaway points is if you care about your information access equality, you should care about not just the network structure, but the spreading process. You are going to have this trade-off between equality and efficiency. Spreading process features are statistically significant. Node and network features are not. And downstream task would be to do the recommendations. For example, you go to Facebook, it says, okay, connect to these people. We recommend that you connect to these people, to connect it, to make the recommendations such that you move your network closer to information access equality. Thank you very much. I know I'm over time. You can download my slides at that URL. I'm happy to answer any questions.
Great, thanks. Thanks for the whirlwind talk. I will open it up for just one or two questions. So I had one sort of provocative question, Tina, which is you sort of offhandedly said that there should be efforts to increase the between group connectivity, which sounds great, but I'm just wondering what are the boundary conditions for that? Because I could imagine situations where if different groups are pursuing different possible, approaches or beliefs or opinions, then it might add to the overall population resilience. So is it always the case?
Yeah, so for us, so it's an excellent question. We didn't think about it deeply. I could see, like in my discussions with, for example, actually I see Steve here and Stephen Lewandowski, and also Bryony, who is a mutual collaborator. That, for example, if you are going to recommend somebody from the other group, you will want to recommend somebody from the other group that has some homophily with you. And that's why, for example, in one of our models, we're looking at people whose neighborhoods are similar to yours. Now we're looking in terms of the network structure, but definitely you're not going to be recommending that I connect to somebody who's very far away from me, right? Because first of all, in terms of utility, like if I'm thinking about it in terms of Facebook, right? I wouldn't connect to somebody who is very, very far away from me, but that you can slowly shift the network. We didn't look at like how long it will take to actually shift the network to a point where, for example, you have this information access equality in terms of that kind of a detail. We did look at homophily, of course, but not specifically the question you're answering. But we'll look at it. Excellent question. I see Phil has his hand up. I would love to hear what Phil has to say.
Thank you. Hi, Tina. So
Hi.
nice to great talk. So yeah, actually following up on Rob's question, this idea of recommending connections to the other side can also backfire. I mean, there is the work by Chris Bale some time ago that showed that that happened on Facebook. So I wonder, I mean, so that's also something to keep in mind.
So I guess the question there is, if I may, just to follow up on that, is like, what does backfire mean? So if I have a piece of information and I just want it to spread, does backfire mean that that information will not spread?
No, sorry. Yeah, no, that's it wasn't even my question, by the way. But anyway, so the point, but it's a really good discussion. I think what they showed is that people then tend to have a more negative reaction to the information that they see from connections that are from the other side. So I'm not arguing about your paper. It was just a comment on the fact that sometimes, like if you consider what people do with the information, it might have an effect that is not the one that we hoped. But anyway, this is super interesting. And in fact, my question was related. It was that what you said in the last bullet of your conclusion, like, about next steps. And I assume that you could try to fit some empirical networks, I don't know, from social media or like the ones that you have, to your model. And then once you infer the parameters, then you could try to use that as an experiment, like to run the simulations on that kind of network and explore different kinds of interventions. Is that the kind of thing that you're thinking about? Any thoughts?
Yes. So both of you. So just one thing. Both of Robert's question and then your clarification and follow up on it. We didn't take that next step, right? Like, to me, that's psychology. But yes, we should take that next, right? What people do with it. It's just like, did Tina see it? Was she exposed to it? Whether she had a negative reaction is a different thing. It's absolutely true that it would be great, and we're looking into it, to take social media data and try to see which model, which of the network generative model fits it, and then try to run these kinds of experiments. The one thing which is interesting is that I may push the network toward information access equality for one piece of information, but take it away from another one, right? Because if I have a simple contagion with symmetric transmission rate, it's very different than if I have a complex contagion with asymmetric transmission rate.
And different messages spread in different ways.
Exactly.
Yeah.
So you can't satisfy all of them, right?
Super
You can make the
interesting.
network better for one thing, but
Yeah.
very difficult for the other thing.
Yeah, very interesting problem. Thank you.
Thank you.
Great. Thanks for the discussion. I think we should transition to Gautam's talk, and then we can return to some of these issues back in a half an hour. So I should point out that Gautam is one of the organizers for this workshop. So it's good to see you here, Gautam.
Thank you. Yeah, so I'll quickly transition. Yeah, as Rob mentioned, I'm one of the organizers, but unfortunately I had to have back surgery a few weeks ago and I missed a number of these talks, but I've attended a few and find them very interesting. The one I'm going to give today is more on learning environments. So it is looking at how people collaborate in technology enhanced environments, but focusing more on learning. So if you don't mind, let me try to bring up my slides and I'll get started. Have that. No. Sorry. Share screen. Put it on full screen mode. Okay, so I'll be talking about the work we have been doing in supporting learners, and this is mostly in K-12 environments. So these are either middle or high school students, but we've also been doing work on analyzing training behaviors when, say, adults train in mixed reality environments. And I'll sort of give you examples of all of those, but then the focus of my talk is going to be on supporting learning in K-12 environments. I have to acknowledge my graduate students, Caitlin Snyder, Nicole Hutchins, who just graduated, Caleb Vattrell, number of others who've done most of the research and the analysis of the data that we've collected. I'm just going to present a summary of those. And most of this work has been funded by NSF grants. So let me see. So in the, as I just mentioned, in the context of this workshop, it's a slightly different sort of twist here. We are looking at how humans collaborate to learn in computer-based learning environments, and this is mostly looking at middle and high school students. And as I just mentioned, we're also studying teamwork, where how groups, in the case of the Army, squads of soldiers, execute dismounted battle drills, or even situations where a group of nurses in a hospital room are collaborating to diagnose a problem a patient is having and then provide the intervention. So just as an example, this is the Army work we are looking at. So you have this particular drill is enter and clear a room. So a squad of about 4 soldiers, as you can see, enter a room and take different positions. And then if they see enemy combatants, they have to neutralize them. They are not supposed to fire and kill civilians. So they have to make some quick decisions. Their psychomotor skills are very important. The way they enter their room, the way they position themselves, the way they coordinate the activities with each other, the communication that they have. So there are a lot of different things that we study, and our approach is, collecting the data, and we are doing offline analysis. Then in this case, it says diagnose, but basically it's inferring and trying to determine, from the video and say other modalities of data that we have, what are the activities that they're conducting, and then through an expert sort of instructor, we provide that information so the instructor can do what's called an after action review, so provide feedback to the soldiers on where they could have done better. And typically in these training exercises, because they're done in augmented reality environments, the soldiers can repeat this exercise multiple times. So the idea is for them to develop what's called muscle memory. So when they're put in a real situation, they can react really fast and while making the right decisions. Similarly, you can see this is a simulated hospital room where at Vanderbilt, they use mannequins to trace and train nurses. So in a typical hospital room, you have a number of monitors where you get information about vital statistics about the patients, the doctor's orders, etc. So in this, in the video or on the left, which is, I just have a still image, you see three nurses sort of studying, the information on the screens. And in this case, they have decided to administer oxygen to the kids. So they're trying to figure out how to get the oxygen equipment started. So we use motion tracking methods, the YOLO-based methods that we have developed further, where we can actually, we put bounding boxes around the different humans, and we can track their movements. We also do additional work, as you see on the right. We can create, the skeletal representations of people, so we can study their pose, and that helps us gain a better understanding of the activities that they are doing, or the interventions that they are performing on the particular patient. And in this case, again, we collect video data, we collect speech data that comes from the videos, but we can also, we've also used additional lapel microphones so as not to have to deal with the speaker diarization problem to a great extent. And so use the combination. And more recently, we've started using eye tracking glasses so we can see where the attention of the nurses are, right? How they're analyzing the information that they pay attention to, and then also joint attention that they're working together. So from just that was just an overview, but then let me get to the main part of my talk. So I'm going to talk about how, say, high school students learn in these open-ended learning environments that we have created. In particular, I'm going to talk about one which is called C2STEM. It's a collaborative computational STEM learning environment. So the emphasis of our work is on getting students to learn science by building computational models. And so in this process, what they're doing is they're not just learning their science, but they're also learning a number of computational constructs. And we are really interested in seeing when students collaborate. So these are fairly complex problems for the students. They have to construct these models and then solve problems using the models. So how they go about co-constructing the knowledge. And following the literature we've come up with to study this co-construction processes, we have to look at the domain-specific processes, and that's where our work is somewhat unique, where we are not just looking at how they're constructing knowledge in one domain, but two of them, right? Both the science, in this case it's physics, and the computation, but how they are combining or integrating. We call that synergistic learning, because they have to combine their science knowledge with the computational knowledge in order to build correct models or debug their models after they build them. Since they're working together, their social modes of interaction are also very important, right? So it's one of them dominating the whole conversation, or they're actually treating each other as equals. What kind of interactions are they having? right? I'll get into the details of that. And the third thing we look at is how are they actually going about constructing their models? And we collect very rich log data from these systems, so we can actually analyze their sequence of activities, and from those we can derive what kind of strategies they're using in the model building process. Are they doing a systematic? Are they dividing up the problem into segments, working on each segment at a time systematically? Are they periodically checking whether the model they're building is correct, or are they just using trial and error methods because they don't quite understand how to construct the model? And in the specific study I'm going to discuss, we had students who were working in pairs as dyads, building these computational physics models. And we were particularly interested in looking at how prior knowledge affected the co-construction processes. So we measured prior knowledge by looking, and let me get to the next slide. So this is what, this explains the experimental study we did. So we did pre-tests in science and computational thinking. Computational thinking is related to computation, to study prior knowledge of the students. And then we looked at using multimodal techniques. So we have video, we have conversations, we use lapel microphones on the students to see how they were collaborating to build their computational models. And then at the end, we had a post-test, which was similar to the pre-test. So we could look at how much science they had learned and how much computational constructs how well versed were they with their computational constructs. So we also had questions which looked at processes, so how well they learned their debugging processes, which again combines both the domain knowledge, in this case physics, and computation. And they did this through a sequence of curricular units that I'll explain in a minute. So let me quickly, because you may not be familiar with this term, open-ended learning environments, let me very quickly introduce you to what we consider our open-ended learning environment. So in these cases, as you may have just noted, students are constructing their models, right, using their knowledge, or they're learning as they're constructing their models. So these learning environments are based on constructivist theories of learning. Then the whole idea is, as they're constructing their models, they're actively constructing their own knowledge of the particular domain. And as I said, in this case, it involves both science and computation. It's open-ended in the sense that we don't direct the students. So there are a number of intelligent tutoring environments that have been built in the area I work in, called AI and education, where people have built tutoring systems to help students learn, say, mathematics. But so given an algebra problem, a student has to go through a sequence of steps to solve an algebra problem. Typically what the tutor does, and this is a computer system, that monitors what the student is doing at each step. But unless the student has got a step right, they're not allowed to move forward. So they're very constrained in the way they solve the problem. In our environments, we leave it very, very open-ended. We don't sort of direct the student as to how to accomplish the task. They just have to build a correct model. They can use their own approach to do it. So this promotes a lot of exploration and reflection, leading to engagement and deep learning. We've seen that in all of the studies that we've run, and it helps students develop self-regulated learning strategies, in specifically metacognition processes. And I'll talk more about that as we go on. So in other words, basically our learning environments provide a learning context and then a set of tools to accomplish their learning goals, which is building a correct model of a scientific process. Here is an example, a screenshot from our system where students are constructing a physics model. In this case, it's a challenge problem where they have to model a truck starting from rest and then speeding up to the speed limit, cruising at the speed limit, and then start slowing down at a particular point, so it can come to a rest at the stop sign. So for students learning physics or kinematics, in 9th grade in high school, this is a fairly complex problem. You can see, they drag and drop blocks to create their model. The model usually it's a simulation model, so they have to first initialize a set of variables. They have to think of what variables to use, and then they have to build the simulation step, which is how the simulation is going to advance in a step-by-step manner to generate the right behaviors. To make it more, domain-oriented, what we've done is, instead of using traditional computational blocks like you might use, say, in environments like Scratch, we have converted these blocks to be domain-specific. So in kinematics or physics, the blocks usually represent, say, position, velocity, acceleration. Students have to use these variables to sort of model a dynamic process of movement of objects. They can, at any time, a partial model or a complete model, they can execute or run a simulation. So they see the animation of the behavior that's generated. If they want to probe into, say, the variables in more detail, they can look at plots of different variables, as you can see in this figure below. So overall, the environment combines instructional tasks, simple model building tasks. We do give some formative assessment, so students can check whether they have learned particular concepts they need for their model building, and it ends with a challenge task. So the particular example I showed you here is a one-dimensional acceleration challenge task, where they have to model an object accelerating, then cruising at constant acceleration, and then slowing down, which is negative acceleration. So we have a number of these units. So the first module is 1D acceleration, then the second module is 2D velocity, so an object traveling at constant velocity in two-dimensional space, and the third one is 2D motion with acceleration. Typically, they solve a challenge problem where a drone, while flying in say, the linear direction, is dropping objects which have to land at certain spots. So it's parabolic motion. So there, in the y direction, there's acceleration. In the x direction, there's only velocity. So they have to decide when to drop an object so that it would land on a particular spot. So these are the different modules that they work on. In this talk, I'll primarily talk about their work in 1D acceleration and 2D acceleration. Oops. So as you can see, this kind of work, they not only have to know their physics to express the relationship between these different variables I talked about, but they also have to know computational constructs like conditional statements. So, when do you switch from, say, accelerating to the cruise mode? When do you start slowing down? So they have to model all those as conditional statements. They, of course, learn how to use variables and update variables. So there are a number of these basic computational constructs that they are learning as they are learning their science. So let me now switch to the collaborative problem solving part. As I mentioned earlier, that we've in this particular study, or in a number of studies, we pair students up to work in one environment. So two students are working with one computer system where they are building models in C2STEM. So just to give you some background on collaborative problem solving, it's defined as coordinated synchronous activity that is a result of a continuous attempt to construct and maintain a shared conception of a problem. And in our work, we adopt a social constructivist approach. So we are not only looking at how they are constructing, the knowledge that they are supposed to learn or use to solve a particular problem, but we're also looking at the social processes, how they interact with each other. So therefore, we look upon this notion of co-construction of knowledge in 3 dimensions. So how are they putting together their domain knowledge processes, the social processes that they use. And in general, it would have been socially shared regulation, but in this work, we are primarily focused on the cognitive and metacognitive processes that students use. And this manifests in the way they go about constructing their models. As I mentioned earlier, we collect a lot of rich log data as students are building their models. So we can infer, what kind of strategies they're using to construct and debug their models. So let me sort of expand on these three dimensions that we are working on. So as I mentioned, when one of the dimensions is domain-specific processes, and this requires them to synergistically learn physics and computation. And you can think of this as having, a variety of different features. So in order for students to collaborate, right, they have to create a shared knowledge space. And the way they do it is they first externalize their prior knowledge, right? And then through discussion, create a shared mental representation of that knowledge. In this case, as I mentioned, it's both physics and computation. And then in order to either construct a model or solve a problem, right, they have to resolve differences in the knowledge that they have externalized. So they have to come to a common ground. And then once they have come to that common ground, then they can start using that knowledge they have to either solve a problem or construct a model, and also to learn new knowledge that they integrate with the knowledge that they already have, so that they can advance in their model building or problem solving processes. So, as I mentioned, we track students' model building activities using log data, but also to interpret the context in which they are doing the activities. We track their conversations, because two students are working together. There's a lot of discussion amongst them as they're constructing their model. And that gives us a much better understanding of their approach and the strategies that they're following. When it comes to social processes, basically, good collaboration implies that students are, creating a symmetric interrelationship with each other. And then, of course, this can include both verbal and non-verbal communication. Verbal is mostly through the conversations that they're having with each other, but it can also be non-verbal. So we haven't analyzed it in detail yet. We intend to do much more analysis. It could be, the gesturing, how much they are looking at each other, how much they are paying attention to what's happening on the screen jointly. So they can be gesturing, they can be pointing, as well as conversations. And social processes would cover, how they're elaborating. So how is one person who knows something sort of elaborating what they knew for the other person? Right? Sometimes it's explanation because the other person has questions. Sometimes when there are differences, two people have two different opinions. How do they negotiate to come to a common understanding? And sometimes there's argumentation. So someone does something one way and the other person might say, but why did you do it this way? Right? I have an alternate approach. So they might have a discussion to see how they can resolve these differences. And this manifests itself as asking questions or seeking clarifications. Like I mentioned, there may be contribution of different ideas, constructive feedback from the partner when one person presents an idea. And then there's this notion of information pooling as through these various social modes of interaction. How do they then put together the individual pieces of information to create that common ground that they can then use for learning further or for solving problems? So as you can see, these social interactions are multifaceted. So we see that students use a variety of features such as attention, emotional state, speech patterns. We haven't really studied emotional state yet. We intend to do that, but we have looked at joint attention and their speech patterns to see how they go about, what kinds of social modes of interaction they use. And then the third one is this notion of shared regulation. In this case, we've looked at joint metacognitive processes. How do they coordinate, right? How do they plan to coordinate? What negotiation do they come up with to come up with a joint plan for solving a particular problem? How do they collectively monitor and evaluate how they're making progress in their tasks? And then we are looking at strategies they're using during model construction, which is combining their science and CT knowledge, as well as debugging processes. So as they're building a model, they don't always get it right away. So what kind of debugging processes do they use? How do they debug? Do they do it by trial and error, or are they using systematic processes? What information do they use on the screen to guide their debugging processes, for example? So here we are, as I said earlier, we're looking at students' model building activities from their log files, plus their discourse, because that gives us very rich information on why they're doing certain actions on the system. So let me get to the study. I don't know how much more time I have. I'll try to finish up in the next 10 minutes or so. So as I mentioned earlier, we were the primary hypothesis or research question in this study was, when students work in pairs, right, how does prior knowledge of the group, right, impact their synergistic co-construction processes, the social interactions they have, and the inquiry and problem solving processes. So given their pretests in science and CT, right, or physics and CT, we could assume that if they had low physics knowledge, low CT knowledge, their prior knowledge is low in both domains. We did not have any students of that kind. So we did a contrastive exploratory case study where we compared 3 groups. So one of the groups had a student who had high prior knowledge in both the science and the CT. So that was and the other student had low prior knowledge in both. So that we call the unbalanced group, but together they had knowledge in both domains. We had another group which was balanced. So one of them was high in science and low in CT. The other one was high in CT, low in science. So we call that the balanced group. And then we had a one domain group as a contrast, where both students were high in their CT and both were low in the science. So they would have to learn the science as they went about their model building processes. So here is just more a quantitative sort of representation of their pretest scores and how we created them. So I'll skip this slide because it's just details on what I said earlier, but just to recollect that we have 3 groups that we are comparing. There's a balanced group that has both, but one each. Then there's the one domain group where both have high knowledge in one, low in the other, and the unbalanced where there's one student who's high in both the domains and the other who's low in both the domains. So again, we are looking at knowledge co-construction, and the way we analyzed it is by looking at descriptive statistics on the summative assessment performance, right, of the student in each group, and how well they were able to construct their computational models. So we had a rubric for scoring the computational models. So we looked at the scores at the end of their model building for the challenge task. Social interactions, we evaluated the students' collaborative discourse, and we looked at 3 particular social interaction processes. One is how they pooled interactions, how they came to a consensus, and joint attention on the tasks that they were working on. And then metacognitive strategy use, we looked at how the sequence of actions they were doing and what kind of strategies they were using for the model construction and debugging processes. The figure below just shows the different sources of multimodal data and how we use that to sort of analyze each of these features. right, of co-construction processes that I've just mentioned. Quickly going through the results, right, it turned out that in terms of learning gains, right, both students in the balanced and the one domain group had good learning gains, whereas the unbalanced group, the low student, though he was paying attention, he or she was paying attention a lot to the high knowledge student, the high knowledge student basically dominated the conversations and the knowledge and the model building activities. The low student did not seem to learn much at all, and even the high student did not have as much learning gains. So, and then when you look at the model building performance on the table below, whereas the balanced and the one domain groups did fairly well. Both of them had a little trouble with the second task, which was the dropping packages from the drone. But both of them did much better than the unbalanced group did. Now, the one domain group, it took them a while to learn the science or the physics knowledge. So you can see that in the first unit, they weren't as good as model construction, but by the time they got to the second unit, they did as well as the balanced group did. So a quick summary is that the balanced and the one domain groups, right, seem to do better in terms of actually constructing the knowledge or learning the knowledge they needed for constructing their models, whereas the unbalanced group did not seem to do as well. When you look at discourse, we again looked at sort of how synergistic were they? Did they combine their science and CT knowledge well? It turned out that, for the balanced group initially, because each student had more expertise in one of the two domains, initially it was non-synergistic. The other student just relied on the student who had more knowledge to provide the knowledge to construct the model. So, but then by the time they got to the final task, which was the drone task, right? They both had more deep knowledge, and the discourse was much more synergistic. It's interesting that since the one domain group, they were both learning their science at the same time. They were synergistic, both in the initial task and the final task, whereas the unbalanced group was also synergistic, and that was because the high knowledge student was dominating all of the discussions and the model building processes. So since he had sufficient knowledge, right, the conversations were very synergistic, but the low prior knowledge student was not participating much. This is a very busy figure looking at their joint attention, the information pooling and consensus building. Given that we are short on time, I'm not going to get into the details. I have a table on the next slide that explains it better. But just as a summary for this figure, collaboration between groups works better when they have similar prior knowledge. And as you can see, if you look at the consensus building and information pooling, right? So the consensus building for all three groups was very, very much integration oriented. So they were trying to combine knowledge from both domains for the model building tasks, whereas for the one domain group initially, because they lacked knowledge in physics, there were a lot of conflicts. So one of the students would propose doing something, the other one would challenge him. But I think it was useful because that helped them learn the physics. When they got to when it got to information pooling, right, there was a lot of interactive externalization. So one of them would say something and then there would be a discussion about it. For the unbalanced group, there wasn't as much interactive elicitation or externalization. A lot of it was constructive externalization because, as I said, one student was doing most of the problem solving, explaining the problem solving process to the other student. when you look at, for example, their use of strategies, right? Again, I'll go through this very fast. The balanced group showed a lot of systematic model construction. So they use this model building in parts, right? They would build part of the model, they would test it and make sure it was working correctly, then go on to build another part. And so this we call systematic model construction, which was a good study. The one domain group, because they lacked knowledge, they did a lot of trial and error initially and throughout. So they would play, which is run the simulation, look at the results, and try to quickly adjust the model, run the simulation again. But in the end, they were successful and they did more systematic construction. And the unbalanced group, it turned out the student with the high prior knowledge did most of the work, as I said. He had to do a lot of debugging on his own to get the model right. And there was clearly a lack of collaboration, because when this student would ask the other student questions or ask him if they were on the right track, basically the other student just quickly agreed or did not respond at all to the high student. So towards the end, for the second task, the high student seemed to do most of the work on their own. So it seems, so as a summary, the larger gaps in prior knowledge between students lead to more ineffective social interactions between them, and then that naturally leads to ineffective model construction strategies. For example, the use of more trial and error in order to try and construct the correct model. So I will skip the summary slide because I think I should stop right now and we should switch to answering questions and discussions. But so just to talk a little about our future work, we have a NSF AI Institute proposal, and my goal is, and we are actually running a study this time where we want to study not just how pairs interact, but classroom interactions, because we see even when we get students to work in pairs, very often students are interacting with other groups, especially when they have difficulties. We want to capture and analyze those conversations. They're often, students are putting up their hands, getting the teachers or researchers to come and explain or help them with certain difficulties that they're having. So really, what we want to study is the social modes of interaction within a classroom, within groups, across groups, how students collaborate, right? And how they interact, how the teacher interacts with the class, how they interact with the teachers, right? So that we can better analyze sort of classroom activities and behavior and provide feedback both to the teachers and students, so that the teacher can improve their instructional processes, the students can become better learners. And we're going to collect a lot of multimodal data, as you see, in order to do these kind of analyses. So let me stop right here. I could not see any of you as I was presenting, but I'll stop sharing. So
great. Thanks a lot, Gautam. That was a great talk. So we can open it up to any questions that people have for Gautam or the pair. I'm tempted to ask you the exact analogous question that I asked Tina.
yeah.
I guess most specifically with respect to what you were talking about. You were talking about the common notion of common ground, and there is this philosophical line of research that we should be transitioning from talking about common ground to pooled ground instead. And the idea of pooling ground is, what do both members of the dyad or all members of a group know together, and that as a resource. And there's times when you can move forward without ever establishing common ground across the entire group, and it becomes increasingly important for areas where there's quite a bit of specialization required in what is known, which might not be the case in your task. But when I think about like what Stephen Sloman was talking about before, where you have to defer to experts, in general, the idea is that real like science tasks require specialization of like the theoretical physicist and the experimental physicist. And there's no real sense in which common ground is maybe achieved. Well, it depends what you mean, I guess. So I guess that's the question. And of course, the tie-in to Tina's talk is I'm sort of grappling towards situations where the diversity, which is kept by not having complete connectivity between the majority and the minority group, actually might serve to help the entire population. Just to put that in the hopper.
No, that's a great question again, Rob. And as part of the social interaction processes, we are looking at information pooling, right? And in this case, we had 3 specific examples, right? So when you have a balanced group where people, one of them has high prior knowledge in one domain and the other in the other, right? We were looking at the differences in how they pooled information, and there were clear differences when you had, disparity between the groups. Where if you generalize it, beyond just 2 students working, you might have one subgroup of students in the class who really understand what's going on, and they have this sufficient knowledge to move ahead in terms of whatever task they've been given. Whereas the other extreme is there's a group that just doesn't understand what's going on at all. So if you generalize from 2 to the classrooms, a lot of these issues that Tina talked about and you're asking about become even more relevant. And I didn't mention this because I was running out of time, but the whole idea of studying this is, you might form initial groups of students to work together. You want smaller groups because you want more discussion and interaction between them, but you also want to open it up when the teacher then sometimes intervenes and there's a classroom discussion on a particular topic, especially if a majority of the students are having problems. At other times, you might want to regroup students because you want to put together students who have similar characteristics, as Tina was talking about, right? They may not know on their own as to how to get together, right? And so that, either the teacher can help them, or, they can then work through their difficulties together. Now, it's a very, in terms of learning, it's sort of very interesting. There's a group of people who've done research and who say pairing a high knowledge learner versus a low knowledge learner is good, because the low knowledge learner learns from the high knowledge learner. At least in this particular case, and in more data that we've analyzed, right, but not written up yet, we don't find that to be the case. And the amount the high knowledge learner learns, right, they are doing a lot of the work, also is much less than when you have these balanced groups, right, and they're working together. So there is some, there is an overlap between what happens, and if we extend out between just a bit to the whole classroom, right, a lot of these issues that you all have talked about in social interaction networks, right, it may not be as extensive as a social interactive network, but you can think of it as a small classroom network where you have different groups, and it's interesting to study the interactions and figure out how to group them so that you can optimize learning for the whole class.
I just wanted to make 2 quick points here in terms of this point that keeps coming up. One is, for example, in the classroom setting, and I enjoyed your talk very much, Gautam, it's fantastic. A teacher can assign people to groups, right? We were thinking in terms of a platform like LinkedIn or Facebook, right? And so if I recommend people to you that you just think, oh, this is crap, right? Then the utility goes down. And so that was why, like, for example, for us, and we were looking at homophily as binary in a way. And of course, you can measure homophily in many different ways. But that if I want information access equality, so then the objective comes in. So the 2 point is who is assigning people to groups, and then the second one is utility, and the third one, I guess there's three, is objective. Like, what is objective just so Tina sees the fact that like there is a monkeypox vaccine, or that like maybe Tina doesn't know anything about it and I just want her to see it, right? And she is in a group that doesn't have as much access to that kind of information.
Yeah, no, that's again a great question, and it's actually an open question, right? Because you know, the advantage of using technology is we can collect a lot more information than, say, the teacher might observe in the classroom, right? Now, in our studies, you know, we get to control who works with whom, and we use prior knowledge to group students. Maybe the teacher might do that, but the teacher might also use other features, right? The social modes of interaction. She knows, you know, which students like to work with each other or comfortable with each other versus which students may not be. So this notion of homophily in our case, right, is a multidimensional space, right? There is the knowledge space, there is the social space, and there is the approach that students use for problem solving. And there can be differences between students in all of these cases. Now, in most cases, you know, the complaint when we use these advanced technology systems in our classroom for teachers is when students are working on the system, they're really engaged, they really like it, but the teacher has no idea what the student is doing. Right, so the teachers want to be part of that process. So a lot of the data we are collecting, it's not that we want to provide that information to the teacher during the instruction process, but allow the teacher to look at it as reflection activities, and then sort of decide, right, what actionable information to take for the next day. Do they want to regroup students? Are there things that they want to discuss with the whole class, right? Or do they let the students work as they would? And then there's also the other issue, right? How much flexibility do you give the students themselves, right? As so the student finds that, hey, I'm not following what's going on in the group I'm in. Can I move over to some other group, right? So these are all interesting questions that we hope we can answer in the future now that we're able to collect this kind of data.
Just dive in, Suparna.
Hi, both talks were really fascinating, so thank you for that. I, in particular, wanted to connect with the finding, Gautam, you reported on strong students benefiting much more from the collaborative learning situation than weak students. That actually doesn't surprise me. That finding is something we have always wanted to pursue in the lab. And so I was very excited to see your data coming from these very ecologically valid situations where you found it. And the reason we've been interested in it is that theories of memory would predict that the students or the participants, as you know, we would say in our experiments, who get to repeatedly retrieve information have a much stronger representation of that information, both in terms of the content as well as how well they have structured that information for future retrieval. So our prediction, this is something we've never tested, which is why I'm really excited by your findings, is that if we were to combine students with weaker prior knowledge and stronger prior knowledge and have them collaborate, many of us would predict that the weaker student would benefit because they are exposed to someone who knows more, but it's actually the person who's doing more of the retrieval and teaching is the one who would benefit based on this enormous literature on repeated retrieval being much better than repeated study or single study, no matter how we cut it. And this is true in the long run, may not be true in the short run. So your findings really map onto all those theories, as well as a vast amount of data there. So it was very exciting to me to hear about that.
Thank you, Suparna. But I do want to make a point. I don't disagree with what you're saying, because it was clear, right, when you paired a low knowledge student, the high knowledge student learned some, but the low knowledge student didn't learn anything, right? Didn't, at least from the pre-post test, right? It didn't show any learning gains. But the point I was trying to make, and ours was a unique case because they had to learn two domains at the same time, is if you pair students, right, who have sort of, in some sense, right, one is high in one domain and the other is high in the other, right? The nature of the interactions, we are really interested in the social interactions, and those social interactions are much richer, right? So it's when you extend. So what you say is correct when you're looking at individuals, but now think of a small group and you have this variety of expertise within the group. Then how do you sort of guide the social interaction such that as a group everyone learns a lot? And we saw that having these somewhat sort of heterogeneous groups seem to provide much more richer interactions than, say, if you had these completely disparate groups. We haven't studied the case of a completely homogeneous group, right? But yeah, so that's a point I wanted to make. So if you extend what you're saying to a group and then you have heterogeneity, right? How do you then promote the social processes such that everyone seems to gain from it?
If I could, I see there are two other questions. So Gautam, I will follow up with you offline because so that others can jump in the interest of time.
Sure. Thank you, Suparna.
Ying, do you want to go first or should I go with my question?
You can go ahead.
Thanks. Yeah, so I was wondering, both of your talks touch on heterogeneity, or Tina's approach in particular is intended to capture and tackle minorities and their access to information. So I guess my question is more general about how we define minority or diversity in a multi-dimensional way, because each node of a network has many different features according to which they could be either in a minority or in a majority. For example, like the race, gender, or some particular beliefs, some expertise in the knowledge. And I guess my question is, how can we approach assessing diversity in a more multidimensional way, or do we even want to do so?
Yes, if I may answer that. So in a way, we pass that buck, right? We're just saying, okay, you give me a social network and you tell me that, like, okay, there are more whites than blacks in this network, right? And so I have my black nodes and I have my white nodes. And it's just basically we rely on somebody else to tell us the division. The thing that we do assume is that when you divide the groups, they're not equal, right? That there is one group that has somehow is more advantageous than the other, just because, for example, there are more of them in the network.
Yeah, I also found, Tina, your talk very interesting and something we haven't sort of investigated yet, which is, so we just looked at prior knowledge, but I think, Rob, you brought this up either directly or indirectly. There's much more to it, right? So it's not just prior knowledge, it's for example, the approach that students take to learn, the background they come from. Right? What kind of background do they come from? Is learning in a particular way encouraged, right? Or is another form of learning sort of encouraged? So really, there are many dimensions that we could pursue, and I would have to collaborate with others because I don't have expertise, especially, for example, if you now start thinking of diversity issues, equity issues, right? Given the background of students, all of which I think would play a role in the kind of studies we are doing. But honestly, I have to admit that we have ignored it. And we've been lucky in the sense that we've had a more homogeneous group of students. But if we went out to different populations, that wouldn't be the case.
And Ying, you may have the final question.
Well, okay, I will make it brief. Thank you so much for your presentation. I really enjoy Tina and Gautam's research. I make my points really quick. It's about the equity, diversity, and inclusion. So for instance, Tina looking at one questions about Tina's research specifically is the current assumption is the majority reaching out to minority versus minority reaching out to majority are getting the same weight. But in the real life, that's completely, I think that's not true because I think the efforts from minority reaching out to majority is much heavier than the vice versa. And also the lower tier people reaching to upper level, it takes more efforts and get less response. And the opposite is, I mean, vice versa. If you hire a position person reaching to lower one, that connection and information spread would be much, much faster. So I don't know methodologically, how can you put in different weights and testing, especially for information spread, like a professor sending an email spread information to students versus students sending an email to the professor to spread information would be completely different.
Yeah, so I appreciate the question. Obviously, there are contexts in which it is exactly as you said, right? In some sense, we are making an abstraction, right? So this was just a simulation of, so our research was, look, you can't just look at the network structure. You have to worry about what information is being processed, right? And the assumption we're making is if I have 100 people in my network, I have more of one type of nodes than another, right? Maybe I have 80 of type 1 and 20 of type 2, right? And then we did look at different seeding portions for the minority, whether the minority has more access to that information or not, right? But clearly there are specific contexts, and for those specific contexts, then, for example, as Phil suggested, one should look at that social network, see which model fits it well, look at the information that's being propagated, classify it, and then go forward, right? If you're talking about a specific context.
Yeah.
So I appreciate the question.
Thank you so much. For Gautam's, it's not a question, it's just thinking out loud. I look at the data, for instance, if we use the gazing data and gesture and facial expression, for example, if the teacher is from an underrepresented group, how those features might different. Also, when the classroom is dominant by one group of students versus another type of group of students, how those features can change. Also, if you're looking at K1 to 12, you actually could looking at by what age the social environment played even more significant role. Like for instance, younger, the less aware of the, the race and gender, but at certain ages, those impacts start to become greater and greater. And also in terms of public, I don't know whether you have the data about social interaction in public versus private. For instance, public in the classroom, like students may, so they may basically interact differently versus they are private, for instance, online only without seeing each other. So I feel the data can, you and Tina can do a research together by looking at, the minority groups learning patterns, just by having the current data, looking at their learning patterns and what is more efficient and what kind of classroom structure, what kind of teacher interactions may not only help the majority, but also can improve the learning of minority. So I think that's all my thoughts.
Yeah, I agree, right? So a lot of what we are planning to analyze, like gestures, etc., right, can be very much dependent on the background that you come from, right? So also speech acts can differ. And so in order to really do this well, we'd have to collect extensive amounts of data from different groups. And that's why I haven't done it as much, but I need to pay more attention to the work that's being done on social network analysis, like Tina's talk and some of the others that were presented earlier, because you all are looking at things on a much larger scale. We have to learn from that and figure out how that applies in the classroom situations.
Yeah.
So thanks for that. That's a very important comment.
Thank you.
Okay, great. Thanks everybody for the very active participation, both on the chat window and in the video. And I look forward to seeing you next week for talks by Danielle McNamara and Nikki Couture. Thanks very much.
Thank you, everybody.
Thanks, everyone.